Okay, all right. Welcome back to the next video of Unit 20. So let me just write, ooh, a little glitch there, Unit 20. Today we're going to be talking about basically the electrophilic addition of a nitrate group to benzene. So what we're gonna see here is, I feel it's pretty important. It's just that how to prepare the nitrate to attack the benzene, because originally in Unit 10, uh, in Unit 10, 10, you would have looked at benzene, and what you hopefully saw was that benzene is a stable atom or molecule. Sorry, stable molecule. And its stability comes from, right? We talked about in Unit 4, we talked a little bit about delocalized electrons. And basically, benzene has a resonance structure. So its resonance structure is that these double bonds can exist, are constantly rotating around the benzene molecule. So if we look at the difference between these two, right, there's no double bond here, and the next second there is a double bond there. So the way that we draw this resonance structure is just, we put a circle in the middle to show that the electrons are fully delocalized around the benzene ring. And right, we said that resonance structures increases, or resonance, basically just resonance, increases the stability of the molecule, and the bonds in the molecule. So since this benzene, right, it's fully delocalized, all of these electrons can not simultaneously, can exist anywhere in this atom, basically, as they rotate around, or in this molecule. So since they can exist anywhere, the reactivity is slightly different than if we just had, a carbon-carbon double bond with, just a carbon-carbon double bond. We had said that this is trigonal planar. Therefore, you can attack from all the way up on top and below. Benzene molecules are planar too, but they've got that additional resonance structure which makes them more stable. So what you should have covered hopefully in Unit 10, I will make unit videos on Unit 10 eventually. I'm just doing this for my class first, but I'm going to make it for the rest of anybody watching these videos afterwards, is that benzene does not readily undergo, so readily meaning, it doesn't really want to undergo addition reactions. You would have seen a bit in the unit for the reactivity of benzene that it prefers substitution reactions. So right, if we've got some sort of benzene ring with a side group on it, sorry, I should probably draw this a little bit better, slow down a little bit. So benzene with some sort of group bonded to the side, we'll just say we've got a chlorine group to the side here, and imagine we send in another a nucleophile. Let's just say even if we had iodine, or even if we had bromine or fluorine, depending on the solvent that we use, the order of which one's a better nucleophile and which one's a better electrophile will change. But in this case, let's just say, so iodine, and here we're going to have a polar aprotic solvent. So in a polar aprotic solvent, a polar protic solvent. So in a polar protic solvent, Iodine is a better nucleophile. So this is more than you guys need to know, but this is just for the example. A better nucleophile than fluorine. If we had a polar aprotic solvent, fluorine would be a better nucleophile. So in this case, I just wanted to define that because I didn't want to lie to you about anything. So with iodine, we'd come in and we'd see a substitution reaction. We'd substitute the benzene ring with the chlorine for the benzene ring with an iodine molecule, or iodine side group, and release a chlorine ion, a chloride ion. So it prefers these substitution reactions, right? The reactivity of the ring, it's not changed in these cases. We're just substituting different side groups onto it. So addition reactions, right? That's where we had, a carbon-carbon double bond, and we brought in, we brought in chlorine gas. And we know that in addition reaction, we add all of this to the double bond. So carbon, chlorine, and 2 hydrogens above and below. So we've added 2 atoms to the double bond. Here we're just replacing the bonding that's already been done. So today what I'm going to show you is how to make benzene react, how we can make benzene react, and this is a very specific circumstance. So and if you read in your textbook, it's gone into depth a lot. So I'd recommend basically memorizing this reaction, just because it's the only. So the reaction that I'm going to show you, let me just change the color, is the only addition reaction to benzene that your textbook even mentions. So if it's the only one, right, you can kind of predict that they will make you know at least one, right? It's not a lot to demand that you know one. You know, if you know they wanted you to learn 30 different ones, then of course, you know, maybe you just need to realize how they react. But in this case, they give you this circumstance. They show you how it reacts. They show you how it withdraws electrons, how how hydrogen gets released, or hydronium ions get released. So we can say that this is probably a very, very important part for your paper 2 and paper 3. So let's go over it. So what we're going to call it, let me just erase this part. It's the nitration of benzene. So for the nitration of benzene, we need a very good electrophile. We need a good electrophile. But these are not easy to come by, right? These are, we have to form these. We have to make them unhappy, because in solution, right, a good electrophile will find a way to take electrons from something else. So we need to force it. We need to do a reaction to make a good electrophile, to make something unhappy, to make it react. So the electrophile that we're going to look at today is NO2 positive, which if we were to draw the bonds, looks like this. And the formal charges, right? If you guys remember how to do your formal charges, how many valence electrons it typically has, minus half of the bonding electrons, minus the lone pairs. So the formal charge on oxygen, this is just hopefully a review for you. Oxygen typically has 6 electrons, minus the amount of lone electrons, 1, 2, 3, 4, minus half of what's in the bond, 1, 2. So it's got a formal charge of 0. This one's in the same state, so it has a formal charge of 0. And nitrogen typically has 5, minus the lone pairs, which is 0, minus half of the bonding electrons, it's 4. So it's got a formal charge of +1. So that's why the basically this nitrate ion, the NO2 ion, has the +1 charge because its overall formal charge is +1. So okay, let's look at how we form this. So it's a good electrophile. And what is a good electrophile? It wants electrons. So that's what an electrophile is. And if we look at these atoms, right, we look at nitrogen and oxygen, we've got very electronegative, and we've got very electronegative. So a very electronegative atom is bonded to two other very electronegative atoms. So based on electronegativity, you can tell how happy an atom is going to be, right? This atom is extremely electronegative. All the atoms are extremely electronegative, but it's got a positive charge. So that shows that something is wrong, right? The NO2 would be happy if it has a negative charge, but right now it has a positive charge, which means that it's missing electrons, but it's extremely electronegative. So we know this is what makes it a good electrophile. So let's go over the reaction for how to form this. So basically, in order to form this electrophile, like nitric acid, HNO3, we'll have a small amount of this nitrate ion in it. But we need to increase that concentration because we need to increase the rate of reaction. So how to do that is that we take nitric acid, HNO3, and react it with sulfuric acid, H2SO4, in order to form kind of an intermediate. It's going to be a weird looking intermediate, H2NO3 and HSO4 minus. So you can see the proton has been donated by, in this case, the sulfuric acid is stronger than the nitric acid. So it forces that hydrogen onto the nitric acid. And then this reconfigures, and this is going to be the third step down here. This reconfigures to release H2O, so we lose one of these O's and these two H's, plus what's remaining, NO2 positive, plus what's left of the sulfuric acid, HSO4 minus. So what's left of the sulfuric acid. So let's look at the actual mechanism. So if I were to draw out this mechanism, I take HNO3, which we draw N, double bonded to an O, single bonded to an O, single bonded to an OH. So that's our nitric acid. This will have a net positive charge. This will have a net negative charge if we were to calculate the formal charges. Or if we want to draw all the electrons, 3, 4, 5, 6, 1, 2, 3, 4, no lone pairs, 1, 2, 3, 4. So there's our nitric acid. And we don't need to know the structure of sulfuric acid because that's not what we care about here, right? We need to care about how we convert nitric acid into the NO2 ion. Okay, so what happens is that this acid breaks apart. So you've got 2H plus SO4 2 minus, because it's a strong acid, it fully dissociates in solution. So this would be fully dissociated. One sulfuric acid can react with two nitric acids. So the next step is that this H comes in and attacks this group right here. So it'll attack the what's it called? The hydrogen donating group. It'll attack the Bronsted acid in this case. So what we get is kind of an intermediate. We get O double bonded to N, single bonded to O with a negative charge. 1, 2, 3, 4, 5, 6. Just let me draw all these lone pairs in. Single bonded to an O, and this is bonded to one H and the second H. So we've got 1, 2. So what we end up seeing here is that this oxygen is unstable now, right? This oxygen, we do a formal charge of this oxygen. Let's calculate it. Oxygen typically has 6 valence electrons, minus 2 lone pair electrons, minus half of the bonding. We've got a formal charge of +1 on oxygen, so he's very, very unhappy with that. So what he does is he ends up taking this double bond away. He ends up saying, you know what, I'm just going to take this double bond and I'm going to leave. You know what, I've packed my bags. I'm going to get out of here. Oh, this is supposed to be only one. Sorry. There we go. So he's just going to say, I'm going to pack my bags. This is a negative. Sorry, I'm just going to change the color. It looked like a double bond, so that's why I tried to fix it, but it's just a negative charge on that oxygen. So he's just going to say, I'm just going to take, you know, how about I just take these electrons and I leave this nitrate, this NO2 by itself. So he's pretty happy doing that. And then now our sulfate is just a spectator. So I'm just going to draw it like HSO4 minus. So the next step, what occurs is that this oxygen steals this bond with the nitrate, and that this oxygen, you know, he's got too many electrons. He's happy to stabilize the inner structure by donating some of his electrons. So he donates his electrons into a dative bond with the nitrogen, while this one takes them away. So instead now, if we look at the structure, right, he's formed a new double bond here. So we've got N double bonded to O, double bonded to O. That's the atom that's the molecule we really want. We had an H2O leave plus H2O, which left off. I'm moving back in with my parents, right? So the H2O left, and then we've got the spectator off to the side, just watching this whole reaction occur, saying like, I did a good job, I donated that hydrogen. So this is how we form that NO2 ion. And then now that we've got that NO2 ion, right, we need to know, I'm just going to tell you here, we need to know this reaction. So we need to know that sulfuric acid donates a hydrogen ion to attack the acidic part of nitric acid. We needed to know that this is the leaving group after we've attacked it. So we formed an H2O leaving group, and that we need to know that this negatively charged oxygen donates his electrons into the center to form the NO2. That's very, like I said, this is the only reaction that your textbook talks about for the electrophilic addition to benzene. So you must know this part. You must know it. Okay, so then we're going to show how this happens with benzene. Okay, so give me a second just to erase it. And then let's show you how this reacts with benzene. Okay, so let's draw our benzene molecule up here. So there's our benzene molecule, and those are, let's just form it as if these are set bonds. Sorry, that's an ugly benzene molecule. There we go, that's beautiful. There we go, we've got a benzene molecule, and we're reacting it with NO2 positive. So it's easier if you draw out the whole structure, NO2 positive. So that's what we're reacting with. So what occurs is that, right, we said that this NO2 is extremely electrophilic. So extremely electrophilic. So what happens is that this bond in here, this double bond in here, will come out and attack the nitrogen. And then these will move onto one of the neighboring oxygens. It doesn't matter which one it moves onto. So the second phase of the reaction, what it looks like is it looks like 1, 2, bonded to an N, O minus, and double bonded to an O. And now this is a resonance structure, right? We've got another resonance structure, 1, 2, 3, 4, 5, 6. He can donate his lone pair in to get rid of his negative charge, and then this can pull the pi bond out, and he can form it. So we've got a resonance structure here, so it's a somewhat stable structure. And before, remember when we draw benzene, you can calculate how many bonds these carbons have. They all have 3 bonds, so they all have hydrogens coming out here. So this is kind of our intermediate. We've destabilized the ring structure, so it's very, very unhappy. We've taken away its full circular resonance structure. We've added a resonance group to the outside. So the next step, what occurs, is that this hydrogen just says, you know what, he is very, very unhappy. I don't want to live next to him anymore, right? So he donates this bond, or basically, or you can imagine the benzene takes this bond back and kicks out the hydrogen, or hydrogen decides, he wants to leave too. So he donates his bond back in, and the last step is that we've got benzene with its aromaticity, conserved, single bonded to the NO2, and we've released the H plus into solution. We've released that hydrogen ion into solution. So we've added an NO2. We've nitrated the benzene ring. So the important parts to know, again, just as a review, important parts to know is 1. Let me change to red. Red is more daunting. 1, how to create the NO2 ion, and the reaction mechanism. So that's HL stuff, right? HL stuff, reaction mechanisms are HL stuff. So showing how these electrons move around is very, very important. So what I should have actually done here I should have drawn the electrons moving to form a bond with the hydrogen, or the hydrogen attacking the electrons and it forming the bond. But drawing the electrons attacking the nucleophile, or the electrophile in this case. It wants electrons, so the electrons need to move to bond, to form the new bond. And 2, what we need is the reaction mechanism for adding NO2 positive to benzene. So we need to know the reaction mechanism. We need to know that the aromaticity, the double bonds contained within the benzene, attack the NO2, which we said was very, very unhappy, a very strong electrophile. Then we show the reactive intermediate. So here's our intermediate. And then they donate the electron back in, and he leaves. So there's our intermediate, and this is the final one. So this is our rate determining step, is the benzene attacking the NO2. So okay, I hope this video was useful. That's basically it for this part, and then we're going to move on to the next part of chapter 20. Hopefully this made sense.